So it's amazing to have Laurent Ameglio here with us today. Laurent's the MD of, I've forgotten it already, EXIGE?
Yes, that's correct.
Which offer geophysical services in the air, on the ground, downhole, and at sea. And today he'll be giving us a rundown on airborne geophysics. So it's going to be a great session. Please use the chat. You'll have the chance to jump off mute and we'll start some discussions at the end of the presentation. So I hope you all enjoy. And yes, thank you so much, Laurent, for joining us.
Okay, well, thanks very much, Jess, for providing the opportunity. Yes, I'm gonna go through the past 50 years of airborne geophysics, giving you a bit of an overview of what happens. And myself, I've been in the industry only for just over 20 years. So let's go through it. And the first few slides, I'll go slowly on some of them. I will not spend too much time. Some of them are just for the background, and that one is a summary you've seen already. That is something that our attorney has been trying to convince me for the past 20 years. Everything I say is world of fiction, okay? But what I show you during the talk is a little bit more than fiction, and what we're doing with airborne geophysics in general. That's my profile. I'm a geophysicist, and I've been now in Australia for 8 years, but I've been in Africa for over 18 years before. And what is airborne geophysics? So basically, the recipe is 4 main parameters. It's first the carrier, then the sensors, which can do the measurements, then the data, and ultimately the end product, which is by far the most important, is information and knowledge. Now, as far as the carrier it's basically an aircraft, and I'll show you now what it is, which we want to have something that is reliable, that is cost effective. And the second one is the sensors. Now that is far more important because it's the hardware that will really record the information that we require. And then you go into the data and the information, which is by far the most important. Carrier and sensors, yes, of course. They are basically toys, and boys like to play with toys, and it's what I've been doing for 20 years, but they are certainly the biggest element of the equation, but they are far less important. Let's go through the airborne carriers. What you have here is what I call the yesterday, today. This is where the airborne geophysics stands nowadays. The HEM here at the bottom and the yellow helicopters are what I call the extinct dinosaurs. Many of those aircrafts are basically transporters. They were never designed in the first place to do airborne geophysics or do survey. They were transporters, but obviously they were available and they were capable to transport big load, heavy equipment. So at the beginning, we didn't really bother about the sensor size and weight. These big aircraft could carry them, but obviously they are getting outdated. They're also getting they are aging. The traditional airborne geophysics, this is the one that is in the industry right now and providing all the supports to the exploration projects. Now, these are aircraft which are not able to do works, for example, the precision farming, which I'll come to later while we reach the paddock. And along the line, you have a couple of innovators, which appears. On the left, you have the first UAVs. These are projects from a big company, Fugro, that was in the early 2000s. So this has been ongoing for quite some time with respect to UAVs. But UAVs, and I'll get back to it later, they never become a streamlined carrier for the geophysics, and I'll show you. Then you have the De Beers attempt with big balloon, and you see on the background that here it's in Botswana, a serious storm, and actually this ended the project because that balloon twisted around his arm there that hold it. Now that's a wonderful platform, very stable, but you need 11 people to run it, so that's not really cost effective. Then you have ultralight aircraft that were used in Canada, very nice design, but very limited capabilities in terms of payloads. And then that's design is the Gyrocopters, which we worked on the past 10 years. GyroLAG is my other company. And I'll come back to this aircraft a little bit later. These are basically where we're going now. This is what I call the today, tomorrow. These are what we call the very light aircraft or the light sport aircraft. This is the aviation which has been more on a recreational side of things, but nowadays they have reached commercial certification, which make them workhorse, just like the traditional larger cousin or airborne aircraft. And you see at the top, it's an Italian aircraft manufacturer, which we're working with. And what is interesting is that these aircraft, you can just remove the wings, put it on a trailer or on a container, and off you go. You don't have to fly long distance. And at the bottom, again, the aircraft on the right, it's a bush aircraft, which has now become a more or less standard aircraft for smaller surveys, and the gyrocopters, which are come again later. And that is where we're going in terms of smaller, lighter, more cost-effective aircraft, which also now have the capacity to transport heavier payload. Now, this is the past 10 years of development we did with gyrocopters. On the top is the normal gyrocopters. So this is a recreational machine. What is interesting here, you see that there is no motor, there's no engine on a rotor. The engine is here on the back. As soon as the aircraft moves forward, the rotor will rotate and it will stiffen and become your wings, just like an helicopter. Now, it's a bit of a different design, was recreational machines. Now, these machines cannot fly 5 hours a day and 7 days a week. Now, the partner Wachtel in South Africa, we decided, okay, we're going to take a bakkie, which here in Australia you call a ute. So it's a 1-ton vehicle, and we're going to make it a flying machine. And you see there 7 or 8 years of various design, and you have here the final prototype, the first final prototype, which is basically an aluminum frame with some cloth around and flying above Joburg. And you have here at the bottom on the left 2 geophysicists, all happy, flying out in central Karoo Desert of South Africa, and behind new machines, and inside a very crude experimental type machine developed. And that was our first gyrocopters, ready to fly a survey. Now, those machines basically fly, as long as you move forward, the aircraft will stay airborne. As soon as you go lower than 50 kilometers per hour, then the gravity calls you back to the ground. So then you push more power. And it's a wonderful machine to fly low and slow in airborne geophysics, which is a requirement for better data. And that was the last prototype. When you see we now move from a front engine back to the back for various reasons. This was experimental. This could get a commercial certification with civil aviation, which is always a big constraint for us in airborne geophysics. We have to obviously get this certificate. And now that's a diagram where to show you where are all of those aircraft. Obviously, the sweet spot in airborne geophysics here, you want to fly low and slow, because you need to be close to the ground to get the better data. Now here, you have a couple of aircraft, all the traditional one, and then a few others that I was showing you, the gyrocopters is here. And I wanted to show you where are the airborne geophysics. So this is the domain of the old traditional aircraft, fly fast, can fly far, they're very big, they're very expensive. The VLA of a sport aircraft is here, and the cost profile of this has evolved from a higher cost from a traditional geophysics down to a much more affordable airborne geophysics carrier, which allows us to do more than mining explorations. And then we can start to attack what I call the anorestic project budget, which is more on a precision farming or environmental application. Now, where to? In terms of carrier, well, the private transport is certainly where we're going. Terrafugia is a company who obtained in January its first airworthiness certificate. Well, I can see, but maybe one day from filling up at the petrol station and going to the airport and take off, and with sensors on board, we could just go geophysics with your own car. That's maybe where we're going. In between, we might have some UAVs. What you have here is a Chinese design. It's a combat machine that was retrofitted with MAC sensors. It flew some 30,000 kilometers apparently in Zambia. We never really seen the data. That was a government project. But this is certainly happening and might happen in the future, as long as those machines can really fly. What we don't see here is that to fly a machine like that, you still need 7 to 9 people. So it's not very cost effective, without to speak about regulations and safety of this machine that can fly up to 10,000 kilometers. Another type of UAVs that is certainly more realistic in terms of airborne surveys. 50 kilo payloads can go up to 1,000 kilometers. It can fly for 12 hours. That might happen as soon as the sky is open for this machine. But look, I'll certainly be retired by the time these things happen, but this is where it's certainly going. Let's go to see the sensors. What I put here is a table with most of the commodities and the 3 major geophysics methods: magnetics, gamma-spectrometric, electromagnetics, EM, and gravity. And in green, basically, we have now all the tools to cover most of the commodities that are explored for, and also physical geology, structural mapping, which we can extrapolate from airborne geophysics data, and I'll show you some example later. The next 4 slides, I'm going to go very briefly, quickly. It's a basic principle of each methods. Gamma spectrometry, what we're doing, we're measuring gamma ray, and we extrapolate potassium, uranium, thorium concentration. The next one is magnetics. That's more familiar. It's a very easy tool for exploration. We're basically measuring the magnetic field of the Earth. The next one is electromagnetic. So electromagnetic is a bit different from the other methods in the sense that we have here a loop below the carrier, or here around the carrier. You see the loop. When we inject electrical current to the ground, there is a response from the ground or any geological deposits, and we're measuring the secondary magnetic field to extrapolate what the deposit is of. And then gravity is another with passive methods. Now, these are the 4 main methods. And now I'd like to show you quickly some of the sensors. Here are the magnetic sensors. These are the traditional one. You can put several of them in some kind of structure to do gradiometry. You have smaller one, the one we developed us with a partner in France. That is 130 grams. This is still 1.2 kilos. You have here Gradiometer. This is what it looks like for measuring gamma ray. And you have here an 100 kilo system. Here it's only 30 kilo system. So a lot of development has been done on the sensors to reduce the size and the weight. And this was mainly due to the UV coming in. And that was very important because it was pushing the manufacturers to develop better technology, lighter, smaller. This is the EM with a loops around the aircraft or towed by the aircraft, by the helicopter, sorry. That's gravity. So gravity, I've seen a lot of progress from several hundreds of kilograms of equipment here in the 70s. And then the next machines here are at 70 kilos. This is scalar gravimeter. And this is a type of gravimeter that is standard in the industry still. That thing is 60 by 60 centimeter. It doesn't fit through the door of a small aircraft. We tried, as we had to change the aircraft at a time and have to redesign the door. But where it is going is these are typical gravimeter. What you have here, it's the Icarus system. It's an inertial navigation system. We are basically measuring acceleration, which is what gravity is all about, measuring acceleration. And that is coming, but as obviously a lower resolution than is typical gravimeter for exploration. So this is not yet exploration grade, I would say. And that is development done by some universities in UK. They're basically trying to use accelerometer in our cell phones just to see if they could use it to measure gravity. And actually, they're already measuring the tides. So that's the kind of developments ongoing. And then beyond the geophysics, and because of a UAV coming in, a lot of equipment that works more with the physics of light. This is a LiDAR. This is a thermal infrared and near infrared combo equipment. This is an RGB camera. And that was another thermal camera with a near infrared camera. All of the systems have been developed for the UAV. What is quite interesting is that with the development of a reduction of the size of the equipment, and at the same time, the development of those light aircraft becoming commercially viable, we could now retrofit UAV type of equipment onto those light aircraft and providing a far better autonomy than what the UAV can do. And that's a very interesting development for the industry. Let's get back close to UAV. You've seen that table earlier. And where are the UAVs? Now, as far as gravity, as I said, it's R&D. It's not there yet. as far as I hear, first systems are coming in, but they will be only replacing ground application. They cannot go very deep compared to any airborne system that can go down to 1,000 meters if we want. UAV gamma, it's getting there. There are systems, but again, 6 to 7 kilos, it's a smaller weight. Magnetics is something that is very much now in the industry. But again, as far as the UAV is concerned, while it's airborne, we don't look at it as really an airborne platform. It just doesn't have the autonomy that any traditional or light aircraft can offer. The UAV is more of a replacement of either the donkey or a ground crew. So that's because a ground crew will walk at 4 kilometers an hour, and that's okay on Monday, Tuesday. As soon as you reach Friday, then they walk a lot slower. That's normal. We get tired. So UAV mag is there, and this is what you see. That's a traditional sensors. Now, interestingly, is that this sensor, the traditional sensors on mag, are quite sensitive to noise about all the rotors. So you keep it hanging there below. That's not really something I ever liked. Us, we developed something different, and we put the mag sensors here at the end of a boom, which the pilots activate. Once he's airborne, it goes down and gets on a vertical position, and then we go surveying. That's much easier, it's lighter, and provide a similar results. What we have done on our side, that some of you might own one, this is a DJI Mavic. It's a small UAV you take to the beach to film a family. Well, we'll do that again soon once we can get out of this lockdown. But what we did, we added a mag system here, and even on the top of it. What we are pushing here, and something interesting, is that we're going towards autonomous UAV. Right now, this UAV mag system, we are at 80% capable of, once it's land, we have softwares to process all the data on site and spit out some data. And the idea here is to have it 100% autonomous, where we have a machine that would be a rucksack, UAV-borne magnetic tools, which are like the geologists to use, just like they use their hammer. And that's something we're very close by to achieve. And talking about autonomous UAV, but this is where we should see soon. What you have here is basically what we call the nest. There's 2 examples I took here. There's quite a few others. What's happened is that you have a UAV that can take off and land back to its platform, the nest, being controlled by any softwares at 1,000 kilometers from here, as long as you have connection. So computers could be programming the takeoff and landing of these UAVs anytime for whatever task. Now, obviously, the problem is, this nest is also the recharging. Now, the problem is that you need 4 or 5 hours to recharge a UAV. So obviously, when it's landed, you 4 or 5 hours, you do nothing. So we'll have to see how these products evolved, where we could have a robotic arm who could swap batteries to go faster, and also to swap sensors, because in geophysics, when geophysics is concerned, sensors are still a bit heavy to be all carried together by only one UAV. But this is where we're going, and particularly for precision farming application. Let's look at some data. What you have here is a couple of photos from a geophysics department here in Australia years ago. What you have here is an electric computer. This is all started. It's here on the back of a deck. And this electric computer was used to transform analog measurements into physical values, which were transcribed on the table, and you was establishing a hand contouring. Then after that came in the digital plotter, then come in the push card computers. Damn, I never have to use that. And then it's where we stay nowadays with PC computers, obviously. And which is much easier, but I have to say that I respect our pioneer to do the work we do nowadays in these conditions. Well, have been a lot of challenge. What is the data? Then what you have in front of you, this is what is the data file from an airborne surveys, and that's only 1 page, and it goes to the right a lot more. And what we do in terms of data processing, when we have to transform these ASCII files into that type of map. This is what data processing is about from Airborne Geophysics. Now, when it comes to data, I'll show you here 2 examples. At the top, on the left, you have raw data from the work we have on our desk right now. It's coming from Tanzania. It's VLF data. It's very noisy. That's normal for VLF data, but it looks like completely unusable. Now, with a bit of a love and care, you can extract a lot of things from data. Same thing at the bottom. Here you have a lot of north-south striping. When you spend time and reuse new algorithm for data processing, and you get a better map, which is more usable for exploration. And I guess what I wanted to say here is that when you have all data, don't discard it. You have a lot of juice you can extrapolate from it still, most probably. And the second point is when you have data in your database system, look at it regularly, manage it. You can extract more juice with a lot of more new algorithm and methods developed for processing. It's very important because at the end of the day, this is your assets. It's not about the airborne survey itself. I'm going to pass that one. What we stand then in terms of data visualization is here on the screen. Now, the problem that we're dealing with 3D data, and obviously our computer screen is still projecting 2Ds. Now, where we would like to be, it's certainly more the avatar movie. That would be wonderful to have an holographic projection of your data. And that might not be complete science fiction. A company in Brisbane, as here on the left, is a prototype of a holographic table, and here you see the final product. Now, obviously, these mesh. So what is interesting here, sorry, for the table, is that you can have two persons interacting. You have small glasses, so you can basically turn the models, move it around. The only problem where we stand so far is that you still cannot interact with the data itself, but this is where it stands. And there's actually a table, I think, at Curtin University. So that's interesting when we can go from there to there and be able to interact and move things in the models and see what it does. That will be a very good progress. But so far, we'll have to deal with our 2D projections of 3D data. Let's move to information. This, what you see, it's again our ugly yellow aircraft we developed, these Gyrocopters, which is one of the best machines in terms of design for flying low and slow. It's not yet fully commercially certified. This thing will not fly in Australia, for example. Australian civil aviation is quite difficult, I would say, and they might have right to do so. But these machines obviously needs time to prove themselves. The problem is that this design was, as a recreational, was flown by people who would enjoy themselves and flew below power lines and these kind of things. And obviously accident happened and the industry has been damaged by those cowboys flying, but it will change with time because they can provide a lot of nice results and at a low cost. It's 10 times cheaper to fly that than any other traditional aircraft right now. Was a survey here. It was in a Barberton area for gold explorations. In fact, it was more a university project. They wanted to structurally map that area here, 20 by 15 kilometers. We flew 100-meter line spacing, 60 meters above the ground. That's a bit high, but as you can see, we had some interesting topography around, so we had to fly around anyway. That is the existing 1 kilometer line spacing. That's very poor data, but it's what is existing in most countries which don't have, like Australia, for example, yet the high resolution cover for most of their country. The rectangle in the middle is the one we flew. And what you see here is this 100-meter line spacing, high resolution. So you can start to see a lot more information from the geology. All the black lines were drawn by the geologist. That is a 3D perspective views of at the top low resolution 1 kilometer resolution data, and at the bottom the new data. That's the kind of magnetic information you can get. That was a university project for the University of Nelson Mandela in South Africa, doing research on this Barberton belt. Getting back to UAV, that's a survey in Western Australia. Now, as I said earlier, the UAV is more kind of a replacement of your ground crew. And what we've done here on the left, you have a ground magnetic data acquired on that area. And on the right, you have what we flew at 15 meters above the ground and 20-meter line spacing. And in the middle, it's basically the ground data, which was upward continued, just to compare. So these two maps should be more or less the same. So that is a mathematic calculation from the ground data. Now, what is important here is that you see good signal without all of those high resolutions, all of those small anomalies are subsurface either human artifacts or data that is of no importance from the geology. So the importance of a UAV there is that you can quickly get that distance from the ground, which you cannot get while you're walking on it. And obviously you don't have to get a bigger machine just to fly a one morning service. That's the importance of UAVs, and it's where they take their right place in a toolbox, not really as an airborne carrier, and particularly when now we have a light aircraft, which are bridging the gap between the traditional airborne geophysics and the ground geophysics. So that's what we can do with UAVs. That is a typical bush aircraft, one of ours. We flew in Uganda, and that's a typical data that you get: potassium, thorium, and uranium concentration, the total count. And here is a ternary, is you merging these three elements together, and that's what we call, it's the first phase of pseudo-geological or physical geology map, which we do, we get from the airborne geophysics data. That was a carbonatite complex, and you can see already the concentric structures. All of those elements here are dry rivers, which we see here in richer in potassium. So that's the type of information you get from gamma spectrometry. The electromagnetic is the Rolls Royce of airborne surveys. It's the equivalent of seismic on the ground. Now it's a little bit more complex to fly. It's bigger system. I showed them earlier in the slides. But what is interesting is that you get roughly a data cube of conductivity or resistivity data. Now you can slice your survey area vertically or horizontally at different depths. So you have a ground surface here is going down to 177 meters, and you can cut down and see different level of resistivity of conductivities for your deposits. As far as EM is concerned, there is, as I said, is a Rolls Royce of a toolbox. There are many systems, and not one system can cover every type of exploration program. So you need to be careful, or need to clearly analyze what you need and to select the right EM airborne geophysics tool. And there's quite a few companies that specialize on a specific technology for a specific target. Airborne gravity, I made the grid in developments. What you have here is ground geophysics. That was a Rutherford Dome in South Africa. It's an impact structure, and all the black dots have a traditional ground geophysics, ground gravity acquisitions. And here the scalar gravity is very comparable. Now you can achieve much faster with a traditional airborne gravity system data over a large area. Now, obviously, the resolution is right now in the industry at 0.3 to 1 milligal over 4 kilometer resolution. And that's for scalar gravity. If you go down to gravity gradiometry, it's here the map compared to the ground surveys, and you see the much better resolution, obviously, from the gravity gradients. And the gravity gradients will give you 0.1 to 0.3 milligal at 0.6 kilometer resolution. So that is becoming a very powerful tool for exploration. It's obviously the high end in terms of price, but this is what is in a toolbox right now. Now, from the data information and into knowledge, what you have here, it's example of RNO exploration we did in Africa. From the MAG and the gamma, usually when you fuse all the data, you can extrapolate what we call here a physical geology map, when you have all of the banded iron formation in dark brown here. And you can extrapolate, or you can, extrapolate, you can identify target zone for further investigations, like here in yellow. On the right-hand side, you can go further, and using the magnetic data, you can calculate the magnetic susceptibility and calculate the source and the depth of the source of the magnetic bodies, and position suggested drill cores for the geologist to decide. Some of the work done by a company here in Victoria, which we work with, PGN, they specialized in structural interpretation of all type of geophysical data put together, the airborne, but also the seismic, and that was one work they did in Gala Craton in Australia. On the oil and gas side of things, the airborne geophysics and particularly magnetics have been a very powerful tool to identify place where you definitely don't want to put your seismic profile and waste a lot of money. Here you have all of those red dots here are magmatic plugs, volcanic plugs, which you want to avoid for your seismic. So all the initial black lines were the seismic plan, and the gray lines are the one that's been adjusted to avoid those things which are of no value for oil exploration. And that was offshore Western Australia work. And obviously down to 3D modeling, that's another carbonatite complex in Africa, which was done by Edgar Stettler, an associate of us, using gravity and magnetic combined together, some voxel modelings, and then some 3D view perspective views of your geological model. This is what we can extrapolate with geophysics to help all the drilling program that will follow. And that drives me from the mineral exploration to the precision farming. And what you have here, it's what's basically imaging what is precision farming about. It's basically replacing the traditional uniform treatment of any agricultural field by looking at all the lateral variations and also the vertical variations that happen above the ground with a crop, but also from a geophysics perspective, the soil itself and underground. And I'd like to show you now a couple of works we did us using this light aircraft, which allows us to fly down to 20 meters above the ground at low speeds and in a much safer way than the traditional airborne geophysics is capable to do with this big aircraft. What you have here, on the right-hand side, some geophysical map. This is a ratio thorium-potassium. And here the total count. And here you have a geological map over a 500-meter diameter. This is a pivot farm. I'm not sure we call in Australia. It's a round field farm with usually in the middle you have a watering system. Now the ground the pedologists have identified two zones separated here by the dashed line. The airborne geophysics, we could identify at least 4 types of soil with only using gamma-spectrometric. Now, when to establish these 2 types of soil, you needed ground sampling for a week, chemical analysis of the soil for another 2 to 4 weeks. You need a month or more to have your results. We flew that small field in less than an hour. The day after, we had already the results. And that's the added value of airborne geophysics. Now, we obviously need to do a little bit more ground proofing just to see what we're measuring, and that's what I want to show you in the next few slides. What you have here is the same geological map we had earlier, these 4 zones, soil zones. Now, if you had electrical conductivity map and also the clay zones identified, then you can start to identify up to 15 different subsoil. At this point in time, we have university students working to find out how does that translate in terms of farm management and crop variations, but this is what we can obtain quickly. From a physics perspective, this soil within a 500 meters diameter is presenting at least 15 different types of soil. What airborne geophysics can do? Well, we have seen on that same farm relationship between thorium concentration versus clay percentage measured on soil samples. And the same thing between total count and sand percentage. Now there's a lot more ground proofing to do. Some of the work in Europe, for example, I've seen thorium related to sand. So there's some work to do, but we start to see a common pattern of relationship that can allow us to certainly extrapolate now thorium into clay content and total count in sand percentage. Now that moves to basically what's happened in the soil. What you have in front of you is basically the soil is not something that is dead. You have a lot of life in it. And what you have in front of you is nematodes. Now these are very interesting. For the past few years, I interacted with biologists trying to understand what are nematodes. Now you have a biologist talking to a geophysicist. It's a very interesting world. Now, but I learned a lot of things with them on this little beastie there, important for farming. And now you have 2 types of nematodes. You have, I understood, the good guys, and these are one are here, microscopic photos. And those guys, basically, we hit bacteria or fungi, and as a byproduct, they release nitrogen, which is good for the plant and a crop. Now, these are the good guys, work towards healthier crop. And then you have the bad guys. These ones are here, they are root feeding. So you have a stillet, this thing gets out, they punch into the roots and basically suck out the cells fluid and obviously kill your crop. And on the right-hand side, you have the predatory nematodes. These ones will hit another nematodes. So you have that war ongoing in the soil, and which is not good, at least these guys, for farmers. And the distribution of the nematodes is understood to be related to the abiotic or the physical parameters of the soil, like pH, clay content, electrical conductivity. And this is what we've been testing to find out with the Airborne Geophysics on that farm. At the bottom here, all different species of nematodes with their names here. They map of distributions. And again, in the lines here represents these 4 zones of soils. Here it's more of a qualitative works, is ongoing with the students in Savannah. We know that these guys are relatively related to electrical conductivity zones. This one is a little bit more doubtful, so there is more work to do, but it's quite positive at this point in time to see that there is a qualitative relationship, and there's quite powerful tools to be getting airborne geophysics and geophysics into management. Another tools which we've been doing at the time is, and that's not geophysics, but it's thermal infrared. As I said earlier, retrofitting this UAV mounted gimbal to the light aircraft allowed us to do something interesting. This is another pivot form, and that's temperature of a surface. So there's at least 3 types of different temperatures we could identify. That was done for training our pilots and testing equipment, as a matter of fact, but we realized that going to the field and checking, we see 3 different types of color of soils, and it was different content of soil, clay. Now, that hasn't been pushed further at this point in time, but with this type of tools now available, not only from the satellite, but at smaller sensors and cheaper to put on board the aircraft with the geophysics, we're getting extra layer of information. And the next one, and I'm almost nearing the end of the presentation, just if I'm still in time, it's Hyperspectral. Now, most of you must be familiar with that. What you have here, it's a work was done with Hyperspectral camera, very expensive, very big, not on a small aircraft, but we can do the same thing with smaller sensors now. But getting back to here, you have here the salt carbon, the silt percentage, the aluminum, and the iron content, extrapolate from the Hyperspectral data and draped over a vertically exaggerated LiDAR DTM model. And what is that? Is basically airborne geochemistry. Now, it looks easy to show the image. There's a lot of work on the data processing. It's not that straightforward, and this is where the industry must work with. But in terms of data acquisition, we are getting now where geophysics plus thermal infrared, near infrared, and Hyperspectral can be flown together as an hybrid platform, which never happened before until recently, because geophysics is flown at a different level than the Hyperspectral system. The new cameras developed for UAVs are developed for close contact, what I call. You don't want to fly, and you cannot fly them above 100 meters above the ground. Now, the light aircraft we use, they're designed to fly 20 to 60 meters above the ground. Now, we have reached this merging of the flying windows, and we can start to think, and it's what we're working us on, to have finally the true multi-physics hybrid system where we have both geophysics tools and Hyperspectral tools to obviously tackle the paddock, but then get back to mineral exploration and to, with one flight, basically get so many data layers. And that, I guess, it's the whole story that I wanted to show about where airborne geophysics was, where we are, when we are going. And well, thank you very much.
Thank you so much. That was a wonderful overview.